Okay, am I audible?
Yes,
Yes, sir.
Thank you. Okay, so let us start today's session. Mm, It's already 6:08. So, welcome all to the live session 3. Um, just the way we have gone through for these earlier two live sessions, same schedule we will follow. We will try to again recapitulate the things, whatever you have gone through in our earlier video lectures, and then we will try to solve few of the few of the MCQ type questions and both numericals also. Yeah, so we will go one by one. Now, what have been covered in your module 3 in the earlier week? So there have been these welding power source characteristics. In my earlier lectures, I had talked about those thermoionic emissions, then ionization, those concepts. We will again go through those things, and then we'll also talk about different kinds of these welding power source characteristics, when you need to use constant current power source, when you need to use constant voltage power source. Those things we will again talk about, right? So yeah, we'll come to the this numerical part later, a little bit later. Before that, let us talk about uh, most on this theoretical aspect, you know. So basically, for welding, you need some kind of heat source, right? Uh, that heat source will release the heat in kind of sharply defined and isolated region, you know. So the heat should be produced at a high temperature and at the same time at a high rate also. And what we know that most common sources of heat include are electric arc. So in case of arc welding, you know, shielded metal arc welding and those things. So electric arc is a kind of heat source. Then you can use chemical flame, whatever is used in gas welding. Then you can have some kind of exothermic chemical reaction that is used in thermite welding. So those things are there. So initially, let us talk about something called emission and ionization of electric arc. So that is the physics, basic physics of how that arc is getting generated, right? So initially, we'll talk about. Let me skip this part for this numerical portion. Over here, I will write down emission and ionization of the electric arc. So first of all, let us try to understand how an electric arc is created and maintained between two electrodes of opposite polarity. So let me first draw something. Obviously, that will be a schematic. That will be a schematic of that arc welding scheme. So you have a power source. One will be connected to your workpiece. So if this is your workpiece, another will be connected to your, what is this? What is this? This is your electrode, right? And over here, your arc is getting generated. This is my, sorry, this is my positive. This is my negative part, right? Now, what does it show? This schematically shows an electric circuit which is used for arc welding, where my workpiece is positive electrode, which is also called anode, and my electrode is negative electrode, which is also called cathode. Correct? Now, what happened? Initially, a good contact is made between this electrode and work. So, the first step is there will be a good contact which need to be done with electrode and the workpiece. That is the first and foremost requirement to generate any kind of arc, right? Now, initially, when you are making this contact in between that electrode and the workpiece, what you will do thereafter that electrode is withdrawn. And whenever you will withdraw that electrode, as a result, what is happening? Some kind of metallic bridges, when it formed because of contact, that will start breaking. So this will create some kind of metallic bridge, and when you withdrawing the electrode, this will be broken. Correct? Till now, any question? Okay. So as a result, I was saying that metallic bridge will start breaking, and what will it result? It will basically increase the current density. So because the bridge is breaking over here, the metallic bridge, it will increase the current density. Correct? Now, finally, if you see, the current density rises to such a high value that the bridges, those metallic bridges, wherever it formed because of that contact, it starts boiling. And under such conditions, the electron come out both of those surfaces, both of these uh, positive and negative surface, and that is what we call thermoionic emission. So this will form some kind of electron bridge of electron. That is what called thermoionic emission, right? Now, obviously, the electrons which are having negative charge, you know, the electrons are having negative charge, that coming out of the anode, which are coming out of the anode, those are pulled back, right? Those are pulled back towards cathode. Cathode attracts the electrons, whereas those coming out of the cathode, those are attracted towards the anode, right? Now, there are some mathematical expression to find out the rate at which the electrons are emitted from a hot surface. So you will have some, if you want to find out what is my rate at which the electrons are emitted from a hot surface. So there are some mathematical expression, c into theta square. Uh, these also have been covered in that video lecture. Where is I over here? I is my current density, right? And the unit is ampere per whatever. It may be semi square or square or meter square. What is theta? Theta is absolute temperature. C is a kind of constant at this function, and beta is a function of phi and theta. So over here, E is my charge of electron, E is my charge of electron, K is my Boltzmann constant, Then what else you have? You have some phi, which is called harmonic work function. So we have some standard procedure to find out what is the work function of different materials. So the work function will vary for different materials. Phi is my thermodynamic work function, and it basically represents the kinetic energy necessary to boil out an electron. Right, the value of phi for some common metals, uh, they can be known, like for aluminium, copper, iron, tungsten, sodium, nickel. For these kind of materials, which are uh, you basically use in everyday purpose, they have some known work function. You know their work function, and from this equation, what can we say? From this equation, what can we say? We can say that a lower value of phi and with a higher value of theta. So if my phi decreases and along with that theta increases, that will make my emission of electrons easier, right? This will make my electron emission much easier if you are working with some lower value of work function of material and higher value of theta, correct? And once this emission of electrons started, uh, the arc itself becomes a source of ions through a process called ionization. So let me rub this up again. So after this thermionic emission, you have some process called ionization. Now what happens during ionization? So those ions will be attracted by the cathode, and there will be kind of collisions happening, right? Those resulting collisions will keep the cathode hot in nature, and the total current in the arc is carried by those two sets of electrons. The first set emitted by the cathode is called primary electrons, and the second set is known as secondary electrons. There are two kinds of electrons, one is primary and secondary, right? And that is produced as a result of this ionization of this arc gap. So ionization of arc gap, what that will result? That will result in collisions of electrons, collision of electrons, both primary and secondary, right? So the generally used electrodes like tungsten electrode or carbon electrode, the primary electrons carry most of the current, whereas with copper, if you are using some electrodes made of copper or aluminium, the secondary electrons carry most of the current. Now an electron, let's say the charge of the electron is E. So let us say I am having charge of electron, which is E, right? And that is moving in an electric field of, let's say my electric field is electric field of gradient capital E. What will be the unit? It will be volt per. the unit of distance. So it can be mm, meter, millimeter, whatever. So basically that electron will experience a force of, what will be the force? My force will be, if my charge is E and the electric field of gradient E is there, which is volt per distance, my force will be this, correct? In other words, what we can say, it basically accelerates at a rate of this. So you know F equal to mf. So what will be my acceleration? E by m, where m is the mass, right? So if it travels through a distance b, let's say, before colliding with another particle, so that can be a neutral atom or another electron, that another particle, it will have a kinetic energy of, this is my force, E into T, right? If it is traveling through a distance d. And this kinetic energy is nothing but the heat, and it manifests itself through some kind of increased temperature. What you see during welding, there will be some increase in temperature. That is because of that change in kinetic energy. And the interparticle collision that takes place in the gap between those electrons, that gives rise to a process called thermal ionization. So this kinetic energy converting into heat, which is called thermal ionization. है ना? So I have talked about this thermal ionization and also thermionic emissions. Now, normally these collisions are kind of elastic, and both momentum and kinetic energy are consumed. If this is elastic in nature, of course, this momentum and kinetic energy will be conserved. And occasionally, it may happen that a collision is such that an electron may be completely knocked out from a neutral atom, right? So which will produce a free electron and a positively charged atom, ion. So that kind of collision, of course, will not be elastic in nature. So there can be two kinds of collision. One is this elastic collision and non-elastic collision. Now, the ions which are produced through this non-elastic kind of nature, those are attracted towards the cathode, as already explained, right? Now, the free electrons, which I was talking about as the secondary electrons, that help the arc to remain electrically conductive. So always the secondary electrons help to remain the arc as electrically conductive, right? And yeah, a definite amount of energy is required to produce this ionization in a given atom or molecule. Anyhow, now now comes the question, how your arc structure will look like, or how will be the characteristic of that arc structure. So if you see it structurally, we can distinguish five different zones in an electric arc. So let's say I'm having electric arc structure. So we can distinguish this arc structure in five different regions. What are those? You can have cathode spot, something called cathode spot. You can have something called cathode space. Then you have arc column. Then you have anode space and anode spot finally, right? If you try to make some graph of how it will look like in terms of arc space versus the potential. So let's say my x-axis is the potential, electric potential, the voltage difference, and this is my arc space, right? So I have regions where graph will be more flat compared to the steeper one. So let's say I use in another color. So this is my, let's say over here I am having cathode. So I'm basically trying to talk about voltage potential difference between this cathode and anode. How will it look like? So over here you are having cathode space. Then this is my arc column, and over here this is my anode space. What is there for cathode spot? I talked about cathode spot first. So this spot is relatively very small area on the cathode surface, which are emitting the electrons. So the cathode spot is a very small area on the cathode surface, which are emitting the electrons. Then comes the part of cathode space. So the space is kind of, what should I say, some kind of gaseous region adjacent to that cathode, and this will have certain thickness of uh, some 10 to the power minus 3 centimeter of order. So the thickness of this cathode space will be of this order, and this region has a positive space charge, right? This will have a positive space charge. And so a voltage drop is necessary as the electrons are to be pulled across this region. You have to have some drop in voltage because this is a positive space charge. And then comes the part of, so is in this companion node. Anyhow, and then comes the part of this arc column. So what you see in terms of arc, that is this part, this arc column part. This is the visible portion of the arc, which is consisting of what you say, this plasma or hot ionized gas, where the voltage drop is not sharp. And then comes the part of this anode space, where again this is a gaseous region of this kind of thickness, which is adjacent to your anode surface, where a sharp drop in the voltage takes place. This is because the electron have, uh, if this is anode, the electrons have to penetrate the anode surface after overcoming those repulsion of those thermoionically emitted electrons, right, from the anode surface. So one is anode, one is cathode. Wherever this is cathode, it will basically try to pull those electrons back. And after anode space, you have that anode spot. So you have spot, you have space, then you have this arc column, which one is visible, and then again for anode there is space and spot, right? So this is how, if we try to figure out what will be the potential drop across an arc, then it will be like this. So the voltage drop uh, shown over here uh, for this given spacing, the current and electrode materials. Now it has been experimentally found. So yeah, we have talked up already about this thermodynamic emission and those things. So it has been experimentally found that if you have some arc length or some known arc length, so for a given spacing, uh, the voltage reduces up to the current value of some 50 amp, and then it increases thereafter. So if we try to draw a graph of how will it look like, so if this is current and this is voltage, this will follow some graph like this. So what I was talking about, that it has been experimentally, it can be different of course, but there will be certain value of current up to which my voltage will be initially reducing and then increases thereafter, right? So yeah, so what is happening is basically up to this much of current where this voltage is getting reduced, the shape of the arc is almost cylindrical in nature. So till this region, there will be cylindrical arc. And what can you say from a cylindrical arc? So over here, the surface to volume ratio of a cylinder decreases with increasing radius, right? So if you are trying to figure out area by volume ratio, it decreases if my R increases. So basically, at this point of time, at this region, a thick and high current arc losses less heat and essentially it burns hotter, right? And this results in a kind of high conductivity as compared with a thin and low current arc. So if you are having a thick and high current arc, in terms of burning, this will lose less heat and it will be more conductive compared with a thin and low current arc, right? And beyond that current value, the arc will basically bulge out and the current path becomes more than the arc gap, which again increases the resistance of the arc. And so these two are contradictory in nature, right? So due to these two opposing effects, uh, that is higher temperature and longer current path, the voltage drop basically remains constant over a wide range of current values. So it kind of almost remains constant. Now, as a first approximation, what we say, we can assume the conductivity of the arc column to be independent of the arc length, and the voltage drop will be linear. So we can say, we can write the voltage drop across that entire arc gap. So if you are having some arc length, let's say if this is your electrode and this is my workpiece and this is my arc length, we can say that this will follow a linear relationship, right? So A is called electrode drop and BL is called column drop, right? Now we will come to the first question part. Do you have any question till now?
Hello? Hello?
Yes. Yeah.
Yes. One thing I want to ask. Just now you said that the thick and high current arc will lose less heat as compared to the thin and low current arc. In reality, what is more preferable? Do we prefer a thick and high current arc or a low current arc?
So initially, it should be a thick and high current where you will lose more, you will lose less heat, and then so I just so till this region, this thick current will be preferable, and after this, you'll work with this thin current because at that point of time, arc will be no longer cylindrical in nature. It will get bulge out, and your resistance will get increased. So
Okay,
those
so
things
this
will
is
change.
actually this is happening already, right?
Yes.
Okay, okay, okay. I thought we do this. No, it's okay. Clear.
Yeah. Yeah.
Thank you.
Okay. Okay. So let us try to do some numericals from whatever we have talked right now. Okay. So my first question says that in a arc welding process, you have measured the arc length as 0.5 meter, right? So my arc length is 0.5 meter, and then I am saying that this is a cylindrical arc which are having diameter of 30 mm, and you know the resistivity of the metal. So this is, let's say, known 2.8 E minus 8 ohm meter, and it says if voltage follows a linear relationship of 20 plus 40 L, where L is, let's say, L is in meter. So you're talking all about SI unit now. We need to calculate the current drawn from the power supply. So what will be I over here? So rho value is known. You know the length of the arc. You know the cylindrical arc dia. You can find out area, cross-sectional area, right, as pi d square by 4. So if you, let's say this is my cylinder and this is my length. I know the resistivity. I know the length. So what will be my resistance? It will be rho into L by A. You know the length and you know the area from cross-sectional area basically. You know from over here. So I will get to know the resistance of that electric arc. And then it says this follows a linear relationship. So at L equal to 0.5 meter, what will be my voltage? So this will be 20 into 40 into 0.5, right? Now if you know the voltage, what will be my current over here? Can you give me a value quickly? I think the concept is not that much complicated. So it's very straightforward. what is my resistance is coming as, if 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 you calculate it as rho L by A.
I put it all, everything in one equation. Just 1 minute. I am near.
Sure.
2.8 into. Uh, it's coming very less. Maybe I made a mistake. 1.48 into 10 to the power minus 5.
The current value.
Yes, it's too less. I made a mistake. Uh,
You must have, have you converted the area to meter square if you have the
no,
calculator?
no, 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 no. 80, 30 mm. I forgot to divide by 100.
Yeah,
Wait.
yeah, yeah.
Wait.
You have
Well,
to
upon
change that
8.
area.
Pi d square upon 4. Okay, that's the mistake I made. Bye. Resistance is 0.09.
Resistance is 0.09. I have not
No.
done anyhow, but your
Uh,
resistance is coming as,
no, 2. Wait, 2.8. I have to get a calculator. 2.8. Yes, yes.
okay, if you do not have calculator as of now, you just get the concept. You can,
Yes, yes, I got the
yeah,
concept. I got the concept.
yeah,
It's straightforward. It's just I
yes,
forgot to do the d square. 30
right,
mm. I forgot to.
right. Okay, so we did this very simple, some kind of numericals. We have one more numerical, of course. Before that, again, just move back to some theory part.
Hmm.
So we have talked about this voltage current relationship of this arc, right? And which determines this required characteristics of this power source, right? Now, let us consider two different characteristics of power source. Uh, you have gone through this constant current and constant voltage power source, where for one case you will have this sharply drooping characteristics, one will be a flat kind of characteristics, right? Now,
Hmm.
if we, let's say, try to gather out some information of what is there, what are the difference between two different kinds of power source, CC and CV. So over here, what will be the rate of melting over here? Over here, the rate of melting will be almost constant. So I'm coming in terms of explanation later. So the characteristic will be sharply drooping in nature, right? Over here, your arc length will remain constant. My arc length will remain constant or constant voltage, right? Then you will have this OCV, which will be higher than the constant voltage OCV. So here OCV is higher than the constant voltage OCV. So I'm just differentiating between
Hmm.
those constant current and constant voltage power source. You'll have this. flat characteristics over here. If this is my arc length and this is my voltage, right? And
Yes.
for this constant current power source, the self-regulation is not available over here.
Not
So this is
available.
mainly used for manual welding operations where you are using some non-consumable electrodes, right?
Yes.
For constant voltage operation, you have this self-regulation of the arc length that is available with an if you are doing some automatic or semi-automatic kind of welding, right? Like some submerged arc welding and MIG kind of thing, right? Now for non-consumable, where you are doing some gas tungsten arc welding, for those kind of cases, you will use this constant current power source. That is true, right? So
Yes.
if I am compiling those differences with what is there in constant current and what is there in constant voltage. Now let us consider two different characteristics of power source. Coming to this explanation part. So let's say I have, so this is my voltage ampere characteristics. So one is, let's say this is one of the arc length. This is another arc length. Let's say this is a flat characteristics of the power source where
Mm.
these intersection points I'm making one as square, one as circle. Okay, these are my two operating points, and another is having a drooping characteristic. Let's say this. Okay, so
Mm.
this is my flat one. This is my drooping one. Over here I have current. Over here I have voltage. This is for an arc length of L. This is for an arc length of L plus delta L. So we have considered these two different characteristics of power source. Now, let's say this is the point A, this is point B, this is point C, this is point D. Okay. Now the
Mm.
curve AB that represents a flat characteristic.
Constant. Yes.
Yeah, that
Constant
represents
current.
a flat characteristic. Whereas this curve CD that represents this drooping one, right?
Mm.
These are my two typical arc characteristics for two different arc lengths. And the intersection of the characteristic of the source and that of the arc that determine my operating points as mentioned as this circular and this square or rectangle, whatever you say.
Mm.
So it can be easily seen that these 2 points are my stable operating points, which are given by the intersection on this right hand side and not by those on which are there on the left hand side. Because uh, if you consider a change, say an increase in the arc current, okay? So if you consider a change in the arc current, let's say an increase in the arc current, the points which are shown by these solid circles, that increase in the arc current causes an increase in the voltage,
Mm.
which in turn will decrease the generator or the power source current also. So basically, any disturbance in your power source will automatically be opposed and the operating point return to their original values if you are considering these working points. However, at the point shown by those solid square just will have those opposite phenomena. So any kind of disturbance, those moves the operating points continuously away from their original location. So yeah, the changes in the arc current for the two power source for a given change, uh, yeah, for a given change in the arc length are also indicated over there. So these are my change in arc current. So over here, this will be my change in arc current, and over here, this will be my change in arc current, right? Now in manual arc welding, uh, you'll have some inadvertent change in the arc length, which is inevitable. So you will there will be always some change. There will always be change in your arc length because you cannot control the melting electrode from yourself because you are doing it manually, right? However, that should not cause a large change in the welding current. So because you don't want a change or a large change in the welding current, for that reason, that sharply drooping characteristic is desirable for manual arc welding. And for a flat characteristic where for a big change in arc length, there may not be any point of intersection between the arc and the source characteristic. If you're having any big change in your arc length, the arc may blow out. So if you want to do some efficient striking of the arc, it is necessary that your open circuit voltage of the source will be high above that operating voltage, and moreover it is necessary to have some quick response of your source, right? So basically it depends how you are feeding your electrode material, and you remain your melting rate as constant, so that there will be there will be not any high amount of change in your current value, correct? So in a semi-automatic arc welding process, what happens, like, you maintain your arc between the workpiece and the wire, which is driven forward at a constant speed as it melts away from the tip, right? That's how it happens in semi-automatic. So an increase in the arc length increases the voltage according to your equation, because that voltage follows your linear relationship, and as a result the current fails, right? Not fails, the current falls. So
False.
yeah, because of increase in arc length, your voltage is getting increased, your current will fall. So yeah, the melting rate being dependent on the current, if you are having an increase in arc length, if my arc length increases, there will be decrease in melting rate, right? And if the reduction in the current due to the increase in arc length is significant, the melting rate decreases considerably so that the arc length return to its original value. So that is how the operation gets stabilized, and a flat characteristic of the power source is desirable in that way, right? Okay. Any question?
No, good.
Okay. So you have those power source selections, right? Like when you should go for some constant voltage power source, when you should go for some constant current power source for different welding process, right? You have those uh, kind of
Yes,
list of tables.
Yes.
shielded metal arc, for gas tungsten, for gas nickel.
Cost, yes, yes. Either we go for constant current or constant volt. For one, I think electro gas we go for both.
Yes, so for
Something like that.
electro gas
Yes.
welding, this is combined in nature.
Hmm.
So yeah, we will go through those MCQ ones. Once I just covered a little bit on these
Hmm.
dynamic characteristics also. Okay, before that, how about doing this numerical? So numerical always will take time. Anyhow, the are very straightforward, whatever we are discussing.
Hmm.
So let us finish the numerical first.
Okay.
So here my question says the voltage current characteristics, again it follows a linear relationship of loss. This
20 L plus 40.
20
Okay,
plus
20
40
plus
L,
40 L.
where L is my length of arc, and it is expected that the arc length will vary between 4 mm and 6 mm. So you have a minimum limit, you have a maximum limit. And
Hmm.
again, it is desired that the welding current will be limited to 450 to 550. For current also, you have a minimum limit and a maximum limit. Then it says I am assuming a linear power source characteristic. So, so what are these two operating points? These two operating points, if this is current and this is voltage, what are these two operating points? So we talked
That
about short circuit current and
yeah,
open
yeah.
circuit voltage,
Hmm.
right? Now
Yes.
it says that uh, we are assuming a linear power source characteristic. So this will follow a relation of V by OCV plus I by SCC equal to 1 if this is following a linear relationship. So this is my equation which you need to
So
solve. You will have two equations, you are having two unknowns.
Is there a relation between the open current voltage and the SCC other than this one?
No, see, we need to find out these two values, right? These two are unknown.
Yes, yes, yes,
So
unknown.
to get two unknowns, we need two equations.
Two equations, yes.
So you have two minimum and maximum limits of length and current. So let's
Okay,
say,
like that. Okay, yeah, I
yeah,
understand. I understand. I took the mean value of 500 and I started solving. Okay, I understand.
yeah,
Then I get two equations and then I can solve for two
yes.
unknowns. Okay, that's how it's done. Okay,
So this is
so
V is
20
20
plus.
plus 14
Right, straightforward. 20 plus 14
plus
to.
this is V1, your V2 will be 20 plus 14 to 6. This is V2, your I1 is 450, I2 is 550.
I got a relation between the two. Open current voltage is 0.42 times SCC.
Sorry, come again.
The open OCV is equals to 0.42 times SCC.
Okay, this is one of your equation.
Yes. The other.
How did you get this equation? Simply by get it from one of that equation, right? 180 by SC OCB plus 450 by SC is equal
Yeah,
to
yeah,
180.
yes, yes, yes.
This will be one of your equation and one will be from the maximum one. So one will be from minimum one, another will be from maximum one. Anyhow, this is straightforward.
Mhm.
You can go through that uh, in your leisure time, maybe. So yeah, we have already talked about those physics of welding part. We have talked about this constant current, constant voltage power source. What is their differences? Why should we use constant current and when should we use? Why should we use constant voltage and when should we use? Lisa, can you mute yourself? Yeah, thank you. So the rest what we have is till now we have not talked about this dynamic characteristics and those feed drive systems, right? You have those electrode feeding system. So let us talk about very briefly on those dynamic characteristics, and then we will move to this MCQ part. So in terms of dynamic characteristics, this is kind of rapid, what should I say, rapid transient variation of your output current and voltage, right? If there is any uh, arc starting or arc reignition kind of situation, you will go for some dynamic characteristics of power source, right? And yeah, so over here, the power units for these short circuits or short arc welding, those usually incorporate an inductor in your output. So the function of the inductor is if there is any instantaneous change in voltage, uh, your rise in current will be much slower, right? So that is what the function of inductor. So if my voltage changes instantaneously, current rise will be slower over there. In other words, what we can say, when when there will be a droplet of molten metal that short circuits the arc, then the voltage changes instantaneously. So that is what the function it is for an inductor. So it is important that there should not be any rapid current increase or what we say current surge during that short circuit, and uh, this would basically result in some kind of electromagnetic force which will cause spatter and oscillation on your surface of weld tool. That should not happen, right? Now, in pulse mode power supply, you can think it of as some kind of DC power source in pulsing mode, right? So, if we try to understand, let me reduce this. If this is time and this is current, and let's say my pulse mode is something like this, something like this. So there are different regions over here. So this is my peak current. This is my I peak. Correct. What is this current? This is called background current, right? Then you have a current pulse. So I peak pulse, and then you have I background pulse. So it is not like that every time you will have this pulse on and pulse off will be similar. It may happen that T on this pulse on time and pulse off time are different depending on your application, right? So basically by applying this pulse mode, you are controlling your metal deposition. So at background current, uh, no metal transfer will occur, but this is set for keeping the arc ignited. So your power source will always have some kind of background current. It will not having a zero current like happen uh, in a AC power source where you are having this alternating current, and you will have that crossover from that positive to negative where you have to cross that zero current thing. Uh, Wherever for a DC pulse mode power supply, you will always have some background current where you are keeping your arc always ignited, and it is set in such a fashion so that your weld pool will remain in molten state at that point of time, right? And your peak pulse current is based on the requirement of your transition current always. That's how it works. Now there is something called this transistor power supply unit. So these are some industrial power supply unit which you have already covered in your video lecture. So yeah, in transistor power supply unit, what are there? This is it contains a transistor or a solid state circuit power supply to regulate your output, or what should I say, or uh, replace the reactors which are found in conventional system, right? And these kind of power supply unit, it consists of a feedback system for regulating your welding parameters. So like the way it happened for any kind of machines where you'll have those closed loop feedback system, you'll get the feedback of this is my voltage, this is my current, this much of heat flux is I am generating. uh, because my temperature is increasing uh, beyond a certain limit, I need to reduce or increase my voltage current in such a way that it will control that arc length or those things. So there will be a feedback system of this transistor power supply unit. Now, the transistor can be made to behave something like a variable resistance, right? So, and the same supply unit can be made to work as a constant voltage source for also for if you are doing some gas metal arc welding or something like that, simply by changing the command signal, and it can be made to give uh, constant current output if you are doing some gas tungsten arc welding. So depending on your application, you can change your uh, power supply unit to either CC or CV from that transistor power supply unit. So I'm not going into the circuit details part. That has been covered in your video lecture. So yeah, and in some cases, this is also used for if you are having any fluctuation in your output voltage, you can compensate that by using those transistor, and that provide you a stable and consistent operation, right? And then you have this wire feeding system for to make the constant arc length system. So you will have this wire feed system. What is there for wire feed system? What are different kinds of wire feeding system we have? You can have a constant speed feed drive system, or you can have a variable speed feed drive system, right? Now, in a constant speed feed drive system, the feed rollers, so you'll have, let's say this is my electrodes, these are my rollers, which are making it moving downwards. This is my workpiece. So the feed rollers, those are rotating at a fixed speed, which is used for this pushing the wire to feed into the weld, right? So as to maintain your arc length constant during your welding, depending on your change in voltage, right? And it is normally used, as I said, with constant voltage power chips. So constant speed feed drive system is normally used for a constant voltage power chips. In combination with, there need to be small dielectrodes where self-regulating arc will help to attain that constancy in your arc length, right? And then in variable speed feed drive system, you will have, so if this is my consumable electrode which is moving downward, so this is two rollers, and you will have something like this, which are the contact tube, and the arc which are getting generated, you can have the sensors to sense those arc characteristics. So in that case, the feed rollers are used for feeding the electrode, just the way you are doing for a constant speed feed drive system, where the only difference is the feed rollers are rolling at a varying speed as per the need to maintain those arc length, like happen in submerged or gas metal, the big thing. And the fluctuation in your arc length, whatever the reason is, because the electrode is melting at some rate, and because of that, always you will have those change in the arc length, and that fluctuation in arc length is compensated by either increasing or decreasing your electrode feed rate, and that electrode feed rate is controlled by regulating that speed of feed rollers, which are powered by some kind of motor, right? And yeah, so those variable speed motor is regulated with the help of a sensor. So where we just takes the input from those fluctuation in your welding arc gap, and uh, provide the necessary information to my feedback system uh, to change my voltage and arc in such a way that my arc length will get stabilized. Correct? So now let us move to this MCQ parts. Okay. So my question two says, which one is correct statement? Can you give me an answer for this? So it says my constant current power supply flows are drooping characteristics. This is true, right? So this is true. Then I say constant current power supply is preferred where non-consumable electrodes are used. Is it true or false? Hmm?
Yes, hello. Yeah,
Yeah.
constant current power supply. Preferred when non-consumable electrodes are used. It is in TIG we use that. So yes, constant current. No, in TIG we use. TIG we use constant. Yes, constant current. True.
This is also true. Correct.
Yes.
Then it says a drooping characteristics as higher.
या शांति रखो.
Then it says a drooping characteristics as higher no load voltage, which is also true. And my arc melting rate will be more stable with higher drooping nature of power source. So this is actually false because
The, the arc melting rate will be more stable with higher drooping rate. Why false? It would more, no? More stable with higher drooping rate of power source.
so what do I mean is let me write this. So let's say you have some kind of drooping characteristics of this. You have some kind of drooping characteristics like this. So I say that arc melting rate will be more stable with higher dripping nature of power source. So is it true for this power
No,
source?
no,
For
no.
this power source,
False.
it will be more stable. For this power source, it will be more stable.
The first one it is more stable.
Which one is the first one? This one? The first one is green one or the red one?
Yeah, the green one. With change in voltage, the current will be less. Delta will be less. That's why, no?
Yes, correct. So
Yes.
over here, for a constant change in voltage, let's say if I am having a constant change in voltage, my change in current will be less over here. So if this is delta I1 over here, and if this is delta I2 over here, delta I1 is less than delta I2. So you need less change in your current, which will provide you more stable thing. Okay. Then I say for self-regulation of arc, which power supply is preferable? This is constant
Voltage.
voltage.
Contrast voltage.
You know this is for constant voltage power source is required for a self-regulation. There I missed one thing as there was one point where you had those combined characteristics of power source. You talked about this EGW, right? Electrogas welding, where we basically provide both constant current and constant voltage characteristics, right? The high voltage portion is the constant current characteristic, and so it will look something like this. Let me draw over here. So for the combined characteristics, if this is current, if this is voltage, this will be something like this. Initially, this will be all drooping character, then it will be flat in nature. So over here you have this OCV, then this is my constant current, nature. This is my constant voltage nature. What is this point called? Any idea?
Transistor trigger voltage.
Trigger voltage, correct. This is my trigger voltage. So below a certain threshold voltage, the power source switched to a constant voltage characteristics. These kind of characteristics is useful to assist, what should I say, to avoid any kind of electrode sticking if it is happening in your weld pool during the shielded metal arc welding operation. Or so usually people use this for EGW operation. Okay. Now, what is a function of a background current in pulsed mode? So we talked about this pulse mode operation, DC pulse mode operation.
Keep the arc on, but self-regulation. Remain the well put in molten state.
So B is correct. B is correct option. This is why we use background current. Anyhow, for DC1 in pulsed mode, you never will have this zero current like the way you get in AC mode operation. There will be those transition from positive to negative, no? So you'll always have this background current over here, as I mentioned. Then I say, uh, in variable speed fit drive system, compensate variation in arc length by increase or decrease of.
Increase or decrease of electrode feed rate.
So your option A is correct.
Yes.
We discussed about question
Mm.
9. And then we say which one of the factors plays a key role in exhibiting the thermionic emission rapidly. So we already talked about a lot about this thermionic emission and thermal ionization process. So it says concentration of electron decreases, temperature decrease, current density decrease, temperature increase, current density and absolute temperature remain same. Which one of this?
Electron emission. Current density increase, absolute temperature increase. B.
Mhm.
Yes, B current density will increase.
Correct.
Yes.
So B is correct. Whenever you're breaking those metallic bridges, you're increasing your current density, and because of those change in current density, I talked about those kinetic energies
Hmm.
which will be generated in terms of that heat, and because of that temperature will also increase.
One question, just one question. Sorry. Here you said something about primary electron and secondary electrons. Can you just quickly tell once again that in tungsten electron we use prime? I didn't get it. Tungsten, we the primary electrons do something, and when we use copper electrode, the secondary electrons do something. What was that?
Just a minute. I'm having a call. A little bit. Just a minute. Yeah, yeah. Sorry for the inconvenience. What did you ask? In terms of primary and secondary electrons.
Yes, you said something that in tungsten electrode.
Yeah, I told that there will be two different types of electrons. So whatever the total current in your arc, that will be carried out by those two. We basically classify those electrons in terms of how much current it is carrying. So um, the first set which, why these guys are joining now? Anyhow, so the first set, what I am classifying is as primary electron, is basically uh, that is emitted by the cathode, and which basically carries more amount of heat compared to that secondary electron. Secondary electron is produced as a result of your ionization process in the arc gap. The primary electrons will remain during those electron bridging thing, and that will basically come out of those cathode spot, and then it will carry more amount of charge of electron. It will produce more amount of heat. And I told that with tungsten and carbon electrodes, if you are using tungsten and carbon electrodes, uh, the primary electrons carry most of the current, whereas for these copper and aluminum electrodes, secondary electrons carry most of the current. It may depend on those work functions which I was talking about. Now there's a that beta value.
Yes, yes, yes. I understood. Yes, the beta value.
Uh,
Uh, the c theta exponential by
yes,
beta.
this one beta value. So it may depend on that thermodynamic work function, and depending on your work material, it may change that which electrons are carrying how much amount of charge of your electrons. It is not standard, of course, but yeah, I may classify depending on your how much electron is how much charge it is carrying the electron. So we classify in that way primary and secondary electrons. That's it really. Anything else?
No, no, clear, clear. Thank you.
Okay, so we will finish it up over here. Thank you for your cooperation, and we'll meet again in the next week.
Yes, thank you.
Yeah, okay. Have a good day. Bye bye.
Have a good day.